Um, Good morning, afternoon, or afternoon. It depends on the country you are located. Um, so, who is speaking here to you is Professor Paulo Roberto Bueno from São Paulo State University. And what I will try to explain to you or discuss with you or introduce a question that we are trying to answer is, can quantum mechanics explain respiration? That's the main focus of this presentation. I'm not saying I will try to answer this question, but I will try to let you think about how uh, we can really deeply think on these situations. So, can quantum mechanics explain biology? It's something that with these questions are obviously quite hard to address, but the idea is to let you think more about that. What is the relationship between quantum mechanics and biology? Part of the concept or content that I will address in this conference is contained in a book that I published few years ago. It's called Non-Scale Electrochemistry of Molecular Contact, in case you are interested in going deep on the science that we are going to discuss on this presentation. So, the purpose of the lecture is effectively to demonstrate that energy storage and transport at the molecular scale applies into two different situations. So if we can understand energy storage and transport at the molecular scale, uh, means that the concept that we have developed in our research group, it applies to two different situations. Molecular sensing principles, which is basically the use of the concepts of energy storage and transport at the interface or electrochemical interface. It allows us to design better applications for medical diagnostics. So one thing is, when I apply energy storage and transport concepts to address, to design a molecular interface, I can apply this for medical diagnostics, and it works quite well. But also the same principles allows us to track respirations, electron transport, which is related to the electron transport at a long range scale of a microbiological colony. So the same principles allow us to understand two different situations, which apparently is not related, but I will show you that the same basic quantum mechanical principles applies for two different situations, or these two different situations. Uh, and obviously, one thing that I'm questioning is, uh, are we able to measure the energy stored and transported associated with the metabolism of living cells? I show you that these questions is something that comes with the analysis that we are going to show to you here. So, starting to describe the importance of electrochemistry through a basic concept, which is the electron transfer rate, or electron transfer, the transfer of electrons between interfaces, or how it works in the nature. It applies for different situations. This was obviously it was a Nobel Prize theory in chemistry in 1992, and it applies for different contexts. For instance, nanoscale electronics, which graphene field effect transistor is one example of applications of nanoscale electronics. Organic electronics, OLEDs, organic light emitting diodes, Molecular sensors, molecular diagnostic and biosensors, which is one area where our group has used the concept that we are developing. Respiration and energy storage device, batteries and supercapacitors is one huge area where electron transfer concepts applies or are needed for us to better understand the properties of this device, and on the photoelectrochemical and solar energy conversion. Um, so let's understand what is the difference of electronics and electrochemistry. The difference between these two fields is that in electrochemistry, additionally to electrons and the lack of electrons, which the physicists call roles. So electrochemistry, besides electrons and roles, deals with ions. So because of this, it changes a lot of our analysis of how is the electron dynamics through interface. And we know that life comes with electrochemistry, not with electronics. So life depends on ion transport and ion screening of the electrons and ion pair electrons. All these phenomena are quite important in for electrochemistry. So what we can say is that nowadays what we are trying to, in terms of applications, obviously, what we are trying to develop is we can see technologically that we have the electronics is quite important for not only memory or storage of information through memories, computer memories or big data issue, and also processing. So the processing of information, not only storage, but the processing of information depends on how we use electronics for make better processors in our computers. So computers, they have a processor, memory, but they don't have sensing, much of the sensing aspect. And in human beings and life in the planet, it has processing, memory, and sensory. So our sensory organs, eyes, ear, nose, mouth, are very important and act as interpreters. And all the signal that we process in our body, the energy that we store, the memory, all the way the communication occurs with the surrounding world depends on electrochemistry. And there is no mobile or mobile device in the planet that doesn't depend on chemical energy. So nowadays we are seeing these big data possibilities and artificial intelligence being combined. I mean, artificial intelligence as a way of processing information, and big data is where the information is stored for AI to process it. But to feed a big data, you need sensory. And so sensors are important at the moment to develop better sensors, especially if the sensors is for stored chemical or biological information. We will need electrochemistry, as we need electrochemistry for and it has become the bottleneck for the electric vehicles, as we know. So any kind of vehicle, it doesn't matter if it is petroleum that we are using, oil, doesn't matter, uh, as chemical energy to be mobile, to be autonomous in this planet, we need electrochemistry. So we know that an electrical car will not work without uh, batteries, lithium ion batteries, and these lithium ion batteries are chemical energy or electrical energy is chemical energy that can be converted into electrical energy to be delivered to the car. So here I demonstrate to you how important is to the electrochemistry to understand the principles and quantum mechanics aspects of electrochemistry. So electrochemical signals of an interface can be used to sensorial purpose. The respirations of a microbiological film can be electrochemically controlled using similar concepts. That's what I will show you today. So let's start to understand to understand a little bit in deep what electrochemistry is. Electrochemistry is electronics, which means an electrode in contact with an electrolyte. Okay, so when we have this type of interface, we have, first of all, in one side, in my left hand here, I have electrodes where we have mobile electrons, and electrons, they are undistinguishable particle, and also degeneracy is typical of the electrons, and it follows the Fermi-Dirac distributions in terms of energy and how energy is distributed with the temperature. In the electrolyte side, or in my right side, I have particles, charged particles, and these charged particles, which are ions, they follow different statistical mechanical distributions of energy. Ions are distinguishable particles, so that's one key point. But what we know for sure is that one phenomena that is well known, or at least well described in electrochemistry literature, is what we call double layer capacitance. The double layer capacitance is a type of electrostatic capacitance where there is only the proportion between the double layer capacitance with the length is the k here, and this k is the length 1 over the bi length, and this length is controlled by how ions are distributed in the interface. So we know how it works, how is the interface here. But the energy that we can store with double layer capacitance means that only because we have ions distributions and how ions are distributed on the interface, it allows us to store energy in a scale that electronics cannot do, or common capacitance or dielectric capacitance cannot do. So it's one thing that nature gives us. That's why we use electrochemistry as supercapacitors or lithium-ion batteries as a way of store chemical energy in a better way. So this is one aspect that electrochemistry offers to us, and this is very different, or in terms of electrostatics, this is indeed is not different but similar to what we saw in double layer. The difference is that in the double layer we have the length controlled by the Debye length, is how ions are distributed on the interface. But in separating charge, between two plate capacitors here, where we have two electrodes, not any kind of ionic chemistry, we can see that again this electrostatic capacitance is only proportional to the dielectric constant of the environment, divided by the separations between these two plate capacitors. And the energy that we stored on here is quantifiable if you know the amount of charge and the capacitance that you have here. So this is something that is well known, but which is less known is that we have also chemical capacitors. So what is chemical capacitor? How is this concept of a chemical capacitor? A chemical capacitor or capacitance is the amount of charge that we have, or you can separate given a difference of potential that you apply. So the inverse of this is proportional to the energy, as we saw previously here. We can show here the inverse of the capacitance is the energy here. So the inverse of a capacitance gives us the energy. If we consider now the separations of charge between two molecules, for instance, it can be an oxidant and a reducing entity. One is receiving electrons from the other, and this is what electrochemistry indeed is. And in this case, at the molecular level, the amount of charge that is separate, in considering the charge, the elementary charge of the electrons is the charge is the amount of charge that you can change. We will see that the energy EdV for a situation like this is proportional to what we call as a chemical potential. So the chemical potential is defined as the variation of energy, or in this case of a molecule, per the amount of electrons that you exchanged. If, for instance, if the exchange is only of one electron, what we have is that the chemical capacitance, or what we call chemical capacitance, is the variation of the chemical potential of the system. So it's directly related with the chemistry of these molecules. So exchanging electrons between two electrodes and exchanging electrons between molecules are quite different in terms of what is the energy that we are computing. And this difference between, and this is the same, can be proved at the atomic level to what we call ionic and affinity energy, ionizations and affinity energy. So the difference between these is really what the variation of the chemical potential is. And the chemical potential for chemists is the negative value of the electronegativity of milking, or can be quantified in terms of ionization and affinity energy. But what I will show you here is that we can measure this, not only computing this as usual, but we can measure this with techniques or electrochemical techniques or electric spectroscopy that I will show you here. We can measure really, in fact, this into interface. So let's considering that now we have the two situations. One is the quantum or the chemical contribution, and the electrostatic contribution for the energy that is being generated in an interface. This is what we call chemical capacitor. It is the series association between the quantum or chemical capacitance and the electrostatic capacitance. Why it doesn't appear like this in the normal physics? because when we try to separate charge between two plates, electrode or a plate capacitor, we note that the definition of chemical capacitance that can be defined as the amount or the inverse of the density of states of your left and right side. You can see that in this situation, in this particular situation, where we have metals and two metal, the chemical energy is not computed. But why? It's because the density of states of a metal is quite higher. This will be zero, this contribution will be zero, and here is also higher. That means that this contribution will be zero because the density of states of the right side is higher. So the contribution of this is zero, and then for this situation, what we call the electrochemical capacitor is only the electrostatic capacitance. But this will be totally different. I will show you that this is totally different if we attached a molecule over the electrode. So it's the same. In this case, it's the same as electrons. Here is if it was salt in the Pacific, and this is the salt amount of salt that we have in Atlantic Ocean. So if I move one truck of salt from the Pacific Ocean to the Atlantic Ocean, I will not change the salt concentration of in one of these oceans. This is the same as we are observing here in this situation, because change one amount of electrons from this situation to this, where we have a lot of electrons here and a lot of electrons here, will not change the chemical of the metals. But if in one of these sides I have a molecule attached to it, is the same as take a spoon of salt and put it into a cup of water. It will be dramatically change the salinity of that cup of that glass of water. So if you put a spoon of salt in a glass of water, it will be a lot of change. It's exactly what we are doing here. If I move one truck of salt to a swimming pool, it will be radically changed. So it's exactly what we are observing here. But in terms of concepts, we know that what we call this here, this K near here, is what we call electron transfer rate here, and this is the electron transport, quantum electron transport. So there is a correlation between this quantum or electrochemical capacitance and what we call electron transfer rate. This G, which is the electron transport, how electron is communicating between two states or two an oxidant and a reducer are different. So the way they communicate is through the transport of electrons, and the transport of electrons is described by this equation. What is this equation? This is just the square of the elementary charge of the electron divided by the Planck constant. This is a coupling term, which is the tunneling. It can be other, but I'm now here just describing the tunneling coupling, electronic coupling between the two states that are communicating each other. This is the degeneracy of the spin of the electrons. This is a constant that is called quantum conductance, or the inverse of this is what we call, for the case where this is 1, or the the coupling between two states are adiabatic, we have what we call the quantum resistance, which is a constant. And we have observed this is the case for electrochemistry. But there is one situation that only electrolytes allows us, means only in the presence of salts that allows us, is that the Coulomb blockade doesn't appear to occur in electrochemistry, where we have the electrostatic capacitance will be much higher than the quantum capacitance, is one situation that we see for electrolytes. And then what we have is exactly that in these situations, I have that the electrochemical capacitance of an interface, in this case, in some kind of interface, is directly proportional to the quantum capacitance of the interface, where the electron transfer rate is exactly this. Okay, and this K, this is the K, the electrocoupling, the coupling, as I told you here, this is the electronic coupling. Then I can write the electron transfer rate simply as a function of the quantum capacitance. So this is one process, and this quantum capacitance corresponds to how we, or what we call sometimes in electrochemistry as the pseudo capacitance process. And this is the way that how we charge this pseudo capacitance is through Faraday current, and so the Faraday current is directly related to the electron or quantum transport of electrons through the situation. So here is what we described, and this is exactly the electron transfer rate can be rewrote if we know, because I know that this is the energy, the squared of the elementary charge divided by the quantum capacitance is the energy. So if this is the energy, what we have is that K is proportional to AH by a coupling process that we call kappa, and this is the energy of our capacitor. If this is the energy of the capacitor, I can write the equation like this, and I will see that the way you can charge an interface can be rewritten in terms of electric current if we consider that electric current is proportional to the electron transfer constant. I can write the electrical current through this interface like this, and I will see that what is no Faraday pseudo or what is double layer capacitance or double layer type of capacitance or double layer no Faraday charging of the interface is one type of current that we found in electrochemistry, and another type of current that I find in electrochemistry is the pseudo capacitance. So this can be also treated in terms of quantum mechanics as a quantum point in contact. So imagining that this is the electrode, this is the molecule coupled to this electrode, I can considering this as a quantum point in contact, where I know that the equation that will dictate the response of the interface is something like this, where we have the electrochemical capacitance and a time constant that is related to our electron transfer rate. So in terms of perturbing in frequency a quantum mechanical process of this interface allows us to understand better how this interface works. So let's go into a more easy way to explain it to you. As I told you before, if we have a molecule, redox molecules coupled to the electrode, and this is in the presence of an electrolyte, what will occur is that this electrostatic capacitance will be so high in the capacitors around these states for these states, this will be too high in such a way that in the one side I have a very huge dense of states, and in the other side I will have just the dense of states of the molecules, or dense of states, or the quantum dense of states of that molecules, or the electron accessibility to quantum states from the electrode. So the quantum capacitance of this interface is directly proportional to the dense of states of the molecules that are bounded to the electrode. That's what we have been studying. So here is the concept. We can investigate the interface using impedance derived capacitance spectroscopy. We call this electrochemical capacitance spectroscopy. That is a way of analyzing the interface. When we saw this, I will show you here one very didactical example. So imagine that we have, in this case, I will show you one example of how modify an interface, a molecular, a metal interface with a monolayer that we can attach a protein containing a redox state. So in this case, what we see in terms of capacitance spectroscopy, the concept of this capacitance spectroscopy is that in the case if I have only the monolayer, the response, the electric current against potential, which we call cyclic voltammetry, is only the red part that of this graph. And in the presence of the protein with a redox center, the response is in green. So we obviously have two electrochemical processes here. One is dominated by the no Faraday's response, and the other is dominated by the Faraday's response. Means in the presence of the protein with redox probe, it's dominated by the Faraday's response associated with this redox center. In terms of spectroscopy, what do we see? We see that if I measure, if I perturb, if I'm in this potential, which we call a potential outside of the redox activity of the protein, if I make an analysis of impedance or spectroscopy, electrochemical spectroscopy, electrochemical impedance spectroscopy in this interface, I will see that only in the presence of the monolayer, I have this red response of I can imagine this peak as an absorption, but this indeed is the absorption of electrons in terms of no Faraday charging of the interface. And in the presence of the protein, but measuring here, I have no Faraday. I'm not accessing any Faraday current, as we can see here, because the response are very similar, only double layer. So what I saw is here in black is only a decrease on this peak of absorption that I called to you. If I measure this in the formal potential or in the Fermi level of the interface, what I will observe is, or obtain as a response, is what is described here in red. What I have here in red is the total response. Okay, so this total response is what I have here. And I can see that the background, if I superpose the measure that I did here in black, I see that there are two coupled response or superposed response. One is the non-Faraday response of the interface, and the other is the Faraday response. If I subtract one by the other, what I have is only the Faraday response. So this is really a spectroscope method of separating any kind of no specific response from the no Faraday response from the Faraday. So I can purify the Faraday response as, and as I told you before, this Faraday response is what I called um, is essentially quantum mechanic. So it's the transport is quantum mechanical and the capacitance is also quantum mechanical aspect. So Faraday response is indeed a quantum mechanical event in at the molecular scale. So how I can obviously describe this much in a much more detailed theoretical aspect if I want. I will not do this for you, but just to let you know that the interface, once you separate it from the no Faraday effects, the way that molecules, redox molecules communicate with the electrode is totally a quantum mechanical event. But um, where is the statistical aspect of the model? The statistical aspect of the model is that each molecule bound to an electrode is treated as a quantum mechanical effect or a rate. This is the rate. The combinations of this resistor, the quantum conductivity and the capacitance of each molecule in the interface, the combination of this will give us theoretically will give us, and considering the quantum mechanics statistics means the KT or the temperature will give us theoretically will give us something like this. Okay, so there is a distribution of quantum mechanical states influenced by the temperature. That's what it really is, and that is the theory. So these previous ones is what theory predicts. This is what theory predicts. And this is what we obtain experimentally, as you can see. Here is what we obtain experimentally. So this is the same monolayer, same chemistry in three different environments, three different electrolytes. Means in red we have DCM, which has uh, a dielectric constant of around 10. Acetylnitrile, which has in green, has a dielectric constant of about 40, and in yellow, what we have is water uh, or aqueous solution where we have a dielectric constant of around 80. And obviously this uh, electrochemical capacitance spectroscopy or impedance derivative spectroscopy, capacitive spectroscopy, allows us to calculate the electron transfer rate, which we can obtain it, and it obviously follows what Marcos has predicted. And I will not tell you how it works, but what I'm showing you is that this is the density of states of the interface, and this is totally reversible, meaning that if I'm measuring this in DCM, I will obtain this density of states, and if I measure it in water, I will measure these density of states, and if I came back to DCM after watching and equilibrium be reached, I will come back to this density of states. So this is showing us how the dielectric external potential of the environment affects the density of states of the molecules over the electrode. In terms of quantum mechanics, as I told you, it's very easy to understand this in terms of quantum mechanics and combined with um the statistical mechanics. So it's very easy to demonstrate that because we are following the Fermi-Dirac statistics, I mean that the amount of electrons that I can add to these monolayers is n, is the roll amount, and the total amount is, if I have one electron per molecule, I will write this as the molecular coverage. So the amount of n by the total amount of molecules, amount of n, which means the amount of electrons that can be added to these monolayers, is if it is if there is one electron per one molecule, if there is one electrons per molecule, the highest amount of electrons that I can add to this monolayer is when n is equal to the molecular coverage. This means that the monolayer here will be totally reduced, and if it is totally oxidized, there is no electrons injected to the molecule, to the monolayer, and then this will be zero. So F is the occupation. So F goes from 0 to 1, and I will show how it works. The capacitance is the amount of charge per difference of potential, and the charge is an amount of electrons charge, the charge of the elementary charge. And here, from a simple analysis, we can see that the n is F per the molecular coverage. So if I substitute this n here, I will cling to this, and if I now derive this and substitute this into this equation, I will see that the capacitance can be written as minus E, the molecular coverage, and the differential of this function F against the potential. This differential equation, or this derivative of this equation of dF against V, is simply E cavity F1 minus F. So this substituted here give us this. And as I told you, if F is equal to 0, means that the film is totally oxidized, and this means this region of this curve. If if the film is totally occupied, then F is equal to 1, and 1 minus 1 is 0. So this will be this part of the curve, and the maximum is when F is equal to half, which means that all these potential, all these functions here, the maximum of the capacitance is in the when we have, or when we are in the formal potential of the electrode, or when half of the electrode is oxidized and half of the electrode is reduced. So is when F is equal to half. The model works quite well. So as we can see here, if I make a molecular dynamic simulations, I have the theory here, the experimental is in here, and the fit to the model, or to this analytical model, which is the quantum mechanical thermalized energy, or the energy that defines the quantum capacitor. If it is thermalized, I can then feed the model to this. Okay, so it works. I can do this more complicated if I want, because all the energy of the interface can be modeled, or the energy of this interface, or the quantum or the electrochemical capacitance can be thought in terms, yeah, can be thought in terms of a Hamiltonian dense of the dense function theory, but I will not go on this deep to you. What I want to show you now, that this equation, this concept, I mean this concept described here, that is quantum capacitance, or quantum capacitors in an interface, or each molecule working as a quantum capacitor in the interface, it applies to molecular diagnostics. So if I design interface using this concept, means if I design an interface where I have molecules here with redox centers, and a biological receptor, and this biological receptor interacts with such a specific target, when there is the interactions, they will change the environment of that capacitance, or the quantum capacitor will be affected, and the way it is affected, I can use it to as a transducer signal for molecular diagnostics. That is exactly what we do. And here you can see that in this case we have redox centers coupled with a molecule or receptors, antibodies that can detect some antigen, and then we can detect these by observing the variations of the capacitance of the interface. And here I can show you how large is the signal, the Faraday signal here, compared with the no Faraday response. Here is the same response I show you before, when we have a protein with redox probe over it. I show you this. This is the response of this interface. The Faraday response is quite higher compared with the no Faraday. And then we can show you that the inverse of the capacitance can be used to construct the analytical curves to detect any antigen or a receptor that is of your interest. It depends on the engineering of the chemical engineering you make in the interface. 1 over capacitance is the energy. So effectively what we are measuring is how the chemical energy of the interface is changing. And because of we have a way of doing these separations of Faraday and no Faraday, and because our method is spectroscopic, it means that it's very sensitive, and we can do better analysis of the interface, which cannot be done with traditional electrochemistry, which is insensitive between the negative control. And here is the negative control, and the negative control using simple electrochemistry will not work. We can do this also in a multiplex way, obviously. Here is the multiplexing analysis of to detect a CRP or PAP concentration is quite different. The selectivity is very high, as we can see here. This is micromolar, is incorrect. This is micromolar here. So micromolar of interference will not affect the variations of the PAP. So we obviously use this concept to develop technologies, and one example is this that I will show you here is the I will show you here one example of how this evolves in terms of technology, or the potentiality of the of electrochemistry. So as I'm a co-founder of a company called USERN Diagnostic, which is a Osler is a company that I'm a co-founder with a collaborators of University of Oxford. I collaborate with them, and so I'm a co-founder of this company, Osler, and we can see how it works. So what do we do really with here? Stop where this benchtop device can be used to pharmacies, in doctor offices, or in emergency department, or in centers where we can diagnose easier, and then this is quite effective as a possibility for the future development of new technology that will come through the electrochemical concepts that I'm trying to teach you here. So as you can see, this is really important. Understand the electrochemical. So this is one example of applications, obviously, of the concepts, and we detect a lot of biomarkers that is indeed important for molecular diagnostics or biosensing. So we have achieved a limit of detections between nanomolar to attomolar levels. So, and we made a lot of, we used a lot of tests that can be done. So I will go now through the last part of my presentation, which is to show you that the same concept that I just taught to you here applies to explain the respiration mechanism of Bacter biofilms. Okay, so is that question: can biological energy be understood? Are we probing life energy? Means that how energy are stored in our organisms. Mm, it is it possible to be modeled by the same energy that is associated with the quantum capacitance? And I think so. So I will try to show you. Geobacter is a bacterial species characterized by its anaerobic respiration, and this is a colony of bacteria that can respirate and produce electricity as it respirates. So notably is the individual ability of Geobacter has to produce electricity during its respiratory cycle, delivering electrons to extracytoplasm acceptors, ultimately turning this microbial cell into a natural battery. So if it's a natural battery, what what's the capacitance associated to it? This has been a huge debate in literature, and I will not go through this, but is a huge debate. Some people call it tunable metallic conductivity in microbial nanowire nanoworks, supercapacitor based on C-type cytochromosomes using conductive nanostructures of bacteria. And so this is just one moment. We will just set my laser point again, and then come back to you. We sorry for this. We'll just come back. Just come back 1 minute. yeah, we are talking about here charge accumulations of electrons kinetics in geobacter sulfur reductus cells, and there are a lot of people discussing the type of conductive. Some say this conductivity is metallic, others say it is cannot be, it is because of redox, uh, is based on redox process, and so both are correct and both are incorrect. So these discussions is that we have this difficulty to understand, to try to explain biological through electronics, but indeed what is electrochemistry? Electrochemistry contains electronics, as we demonstrated here, in terms of the energy or in terms of what we call electrochemical capacitance, because electrochemical capacitance can approximate to electrostatic capacitance, or it can go to quantum capacitance, or it can be intermediated between these two. And what we observe, how we model this, we measure the electrochemistry of these geobacters, sulfur reductus geobacter cells. And the model that we come out to this is that we come with a model that's quite simple. It's here is the impedance response, and the capacitance can be very huge. For the colony, it's 3,000 microfarads per centimeter squared. So this is huge capacitance. And but at the end, what we have is a similar pattern that we found in our molecular films, but expanded into 3 dimensions. So the model that is modeling these films that or can be used to model these films is quite similar to what we observe in that interface, with a difference that we need to considering an interface that is distributed along of a long range length in the film, and this causes a decrease in the or there is a potential gradient, but this potential gradient is because of a transmission line, but the element that is contained in this transmission line is quite similar and carries on the electrochemical capacitance. So in doing this, I will come back to the equation that explain the density of that molecular film. And one simple approximation is the case that electrons now are moving through the exocytoplasmatic receptors outside the film. Basically is this one. So these exocytoplasmatic cytochromes here follow outside of the cell, works as like a semiconductor band, or semiconductive band inside semiconductor. And as we know, electrons transport through semiconductors or in the conductive band of a semiconductor follows Boltzmannian behavior. So considering f much lower than 1 is the same as considering f as or electrons in the band or through this exocytoplasmatic path, is the same as considering electrons as with a Boltzmannian behavior. And this implies that we can then approximate these equations to this equation, and then rearranging this, I will show you that we can show you that the energy or the free energy that is accumulated in the microbiological film is the ratio between the electrochemical capacitance in a certain energy state of that interface over a maximum capacitance where we have the maximum cytochromatic or cytochromical receptors, cytochromical receptors uh, uh, fully occupied. So if it is fully occupied, there is a maximum capacitance, and then only considering this maximum capacitance, we can then fit, the model fits the current potential energy, current potential curve of acid of these geobacter films, and also so the model applies quite well to explain the this problem. Okay, so as a final remark, what I'm showing you here is that nanoscale electrochemics or quantum mechanical or the quantum mechanical descriptions of the electron transfer rate constant that includes the quantum capacitance on it allows us a better understand of the electron transport energy storage in biological respiration chains of a biological film that served us as a model, and also it can be used to produce man-made interface for molecular diagnostics. So this allows us, from a scientific point of view, understand the mechanism involved in the device, and from a technological point of view, which is the applications of the scientific knowledge, allows us to control and improve the device. Means we improve the device like biosensing, as I showed you in this presentation. So I would like to thank you very much for your attention, and I'll be available for comments or any response that you want. Just please contact me, then I can address any questions that come to you during this conference. Thank you very much, and thank you all the organization of USERN for inviting me to give you this presentation. Thank you very much.